277 years. That is how long it would have taken the United States to build the tanks it needed for war. 18 months. That is how much time the world was willing to give it. In the summer of 1940, those two numbers defined America's future. One meant defeat so total it wouldn't even be remembered as a battle. The other meant survival, if survival could be manufactured. Across Europe, German armored columns were already deciding the fate of nations in weeks, sometimes days. Poland collapsed in less than a month. France followed in 6. Steel moved faster than diplomacy, and numbers mattered more than courage. In Washington, the arithmetic was unforgiving. The United States Army possessed just 66 medium tanks, not divisions, not battalions. 66 machines, each one slow to build, difficult to replace, and painfully unique. At that production rate, the war would be over long before America ever arrived. On June 7, 1940, a telephone rang inside Chrysler headquarters in Highland Park, Michigan. The man on the line was William Knudsen, President Roosevelt's newly appointed Commissioner of Industrial Production. He did not ask about designs. He did not ask about experience. He asked a single question. Can Chrysler build tanks? On the other end of the line, Chrysler President K.T. Keller paused. Then he answered with complete honesty. I don't know, he said. I've never seen one of these things. The call lasted 7 minutes. By the time the receiver was placed back on the hook, the clock was already running. In June of 1940, the United States looked powerful from a distance. It had factories, steel, oil, railroads that crossed a continent, but beneath the surface, its military strength was dangerously thin. On paper, the U.S. Army ranked 19th in the world, behind nations most Americans could not have found on a map. The Army owned fewer than 70 modern medium tanks. It owned more horses than armored vehicles. Cavalry doctrine still shaped planning in an age that had already moved on. Across the Atlantic, war had revealed a brutal truth. Battles were no longer decided slowly or even primarily by infantry. They were decided by speed, by coordination, by armored formations that punched through defenses before commanders could even react. Germany did not win because every tank was perfect. It won because it had enough of them in the right places at the right time. The United States did not. American tanks, such as they were, came from government arsenals that still operated as if the First World War had never ended. Each vehicle was built almost by hand. Armor plates were fitted individually. Parts were machined to loose tolerances and adjusted by eye. Skilled craftsmen compensated for variation through experience rather than measurement. No two tanks were truly identical. At the Rock Island Arsenal in Illinois, working at full capacity, the United States could produce perhaps 3 medium tanks per month. Each one required roughly 12 weeks from raw steel to completion. Every delay cascaded. Every mistake required rework. Speed was impossible, not because workers were slow, but because the process itself was. This method had worked when tanks were rare, experimental weapons. It collapsed the moment tanks became decisive. By comparison, Germany had already built thousands. Britain, despite its own struggles, produced tanks by the hundreds. Even those numbers were proving insufficient, as losses mounted faster than replacements could arrive. The danger facing the United States was not invasion, it was irrelevance. Wars are not won by what a nation can build eventually. They are won by what it can deliver now and replace tomorrow. By the summer of 1940, the mathematics were already clear. At its current pace, America could not fight a modern armored war. It could barely participate in one. And yet, no one in Washington had a better answer. The arsenals could not go faster. The system could not scale. The methods were treated as fixed, almost sacred. The problem was not courage. The problem was not money. The problem was that the United States was trying to fight a 20th century war with 19th century production. And somewhere in Michigan, a group of men who had never built a tank were about to decide whether that assumption was actually true. To understand why America could not build tanks quickly, Chrysler's leadership went to see the process for themselves. At the Rock Island Arsenal, tank production did not look like manufacturing. It looked like craftsmanship. Armor plates were lowered into place and adjusted by hand. If a plate didn't quite fit, it wasn't rejected. It was modified. Holes were widened, edges were ground down, components were machined again and again until they finally aligned. Nothing was standardized beyond rough dimensions. Every tank became a one-off. Creation. Tracks were tensioned by feel. Drivetrains were installed through trial and error. Welds and rivets were judged by the eye and experience of men who had spent years learning the trade. This was not inefficiency. It was mastery. But it was mastery that depended entirely on individuals. The result was predictable. Production could never exceed the number of skilled craftsmen available, and skilled craftsmen could not be trained quickly. Lose them, and production slowed. Expand demand, and nothing happened. Each medium tank required roughly 8,000 individual components, most of them built to tolerances so loose that final assembly depended on adjustment, not precision. Every delay multiplied, every mistake consumed days. When Chrysler engineers calculated the numbers, the result was almost absurd. At 3 tanks per month, producing the 1,000 tanks the Army requested would take more than 2 centuries. 277 years. That was not a projection. It was a certainty, if nothing changed. K.T. Keller summed it up with a blunt observation after watching the work unfold. "This isn't manufacturing," he said. "It's sculpture." And sculpture, no matter how beautiful, could not win a modern war. The question was no longer whether America could build tanks this way. The question was whether tanks actually needed to be built this way at all. The question reached Detroit on June 7, 1940. William Knudsen, President Roosevelt's newly appointed Commissioner of Industrial Production, picked up the telephone and called Chrysler headquarters in Highland Park, Michigan. Knudsen knew exactly how bad the numbers were. He also knew the government arsenals could not fix them. So he called the people who understood production better than anyone else in America. When K.T. Keller answered, Knudsen did not ease into the conversation. He did not talk about doctrine or long-term planning. Time was already gone. He asked a single blunt question. "Can Chrysler build tanks?" There was a pause on the line. Keller did not pretend. He did not exaggerate Chrysler's capabilities. He did not offer reassurance he could not guarantee. "I don't know," he said. "I've never seen one of these things." For a moment, that should have been the end of the conversation. Chrysler had no tank designs, no tank factories, no experience with armor or turrets or battlefield requirements. By every traditional standard, the answer should have disqualified them immediately. But Knudsen wasn't calling for tradition. He was calling because Chrysler knew how to build complicated machines at scale, millions of them, every year, with parts that fit together not because someone adjusted them, but because they were made to fit in the first place. The call lasted exactly 7 minutes. By the time it ended, nothing had been designed. No factory had been planned. No production line existed. But the problem had quietly shifted. The Army was no longer asking whether Chrysler knew how to build tanks. It was asking whether tanks could be treated like something else entirely. When Keller hung up the receiver, he did not call the Army back. He called his engineers, and within the hour, a group of men who had never built a tank were gathered in his office, about to decide whether American industry could do something no military arsenal had ever done before. Within days of the phone call, Chrysler's senior engineers traveled to the Rock Island Arsenal. They walked the production floor slowly, watching every step, every pause, every adjustment. What they saw confirmed their worst fears. A tank did not move down a line. It sat in place while men moved around it. Work stopped constantly, not because of mistakes, but because parts rarely fit the same way twice. Armor plates arrived slightly warped. Holes were misaligned. Shafts varied just enough to force remachining. Nothing was wrong with the workers. They were highly skilled, careful, and proud of their craft. But everything depended on judgment, on feel, on experience accumulated over years. That dependence was the problem. A craftsman could compensate for imperfect parts. A system could not. And wars are not fought by craftsmen. They are fought by systems. Chrysler's engineers began breaking the process down. They measured how much time was spent assembling parts and how much time was spent adjusting them. The results were staggering. Well over half of all labor went not into building the tank, but into making mismatched components behave as if they belonged together. Every tank required constant decision-making. Every deviation slowed the entire build. There was no way to divide the work cleanly, no way to train new workers quickly, no way to multiply output without multiplying years of experience. One of the engineers finally said what everyone else was thinking. This can't scale. You could double the workforce and gain almost nothing. You could pour in money and still be limited by human judgment. You could demand speed, but the process itself resisted it. At this rate, even if America started immediately, it would still be building its first real armored force long after the war had already been decided. For the first time, the problem became clear in its full shape. The United States did not need better tank designs. It did not need more skilled craftsmen. It needed an entirely different way of building. And that meant asking a question no arsenal had ever seriously considered. Not how to make tanks stronger, not how to make them better, but how to make them repeatable. Back in Detroit, the engineers gathered around a single uncomfortable conclusion. Trying to build tanks faster was pointless. The process itself was the enemy. So they stopped asking how to accelerate it. Instead, they asked something far more dangerous. What if tanks were being built the wrong way entirely? Owen Skelton, Chrysler's chief production engineer, was the one who finally articulated it. He did not speak about armor thickness or gun calibers. He spoke about weight, parts, and repetition. An automobile, he said, was roughly 2,000 pounds of steel, rubber, and glass. It was assembled from about 5,000 individual components. Chrysler built thousands of them every single day. A tank was 30 tons of steel, assembled from roughly 8,000 parts. The difference was scale, not complexity. That realization reframed everything. If an automobile could be broken down into standardized parts, assembled in sequence and repeated endlessly, then a tank could be as well. There was nothing mystical about it, no hidden craftsmanship embedded in the steel. The problem was not the machine, it was the assumptions surrounding it. Military engineers treated tanks as unique weapon systems, each one deserving individual attention. Chrysler. Engineers saw something else entirely, a mechanical assembly that only looked special because no one had ever tried to build it any other way. If tanks were treated like machines instead of monuments, everything changed. Parts could be built to precise tolerances instead of being adjusted later. Assemblies could be broken into modules. Work could be divided into simple, repeatable tasks. Quality could be measured instead of judged. Speed would no longer depend on experience. It would depend on design. This was the moment the real gamble began. Because if Chrysler was right, tanks could roll off assembly lines just like cars. And if they were wrong, the United States would lose precious months chasing a fantasy, while the war moved on without it. Once the question had been reversed, the solution followed with ruthless logic. If tanks were machines, then they would be built like machines. The Chrysler method began with a decision that seemed small, but wasn't. Every component would be manufactured to precise, automotive-style tolerances. Not loose enough to require adjustment, tight enough that parts either fit or were rejected. This alone challenged decades of military thinking. Tank components were massive. They absorbed shock, heat, and vibration. Ordnance engineers insisted that precision manufacturing belonged in civilian factories, not on the battlefield. Chrysler disagreed. Precision, they argued, did not weaken a tank. It removed uncertainty. If every part was identical, every assembly step could be planned. And if every step was planned, speed became predictable. Next came interchangeability. Armor plates would no longer be custom-fitted. They would be standardized. Hull sections would be welded in fixed jigs that locked geometry in place before a torch was ever lit. Turrets would mount on uniform rings. Drivetrains would be built as complete units, tested and installed as a single module. The tank would move. The workers would not. Instead of craftsmen gathering around a stationary vehicle, Chrysler proposed a moving assembly line. Each worker would perform one specific task over and over again until it became automatic. Skill would be embedded in the process, not the person. This was heresy to the Ordnance Department. Welded armor, they argued, was unproven. Rivets had been used for decades. Welding introduced heat stress. Welding required skilled operators. Welding could fail catastrophically under fire. Chrysler answered every objection with tests. Welds were fired upon, joints were measured, failure points were studied. Welded armor did not weaken the hull. It strengthened it. And unlike rivets, welds did not turn into lethal fragments when struck. As for skilled labor, Chrysler had an answer for that too. If parts were held in position by jigs and procedures were fixed, then welding no longer required years of experience. It required training, weeks, not decades. Quality control would change as well. Instead of relying on judgment, inspectors would rely on measurements. Gauges replaced intuition. Deviations were caught early, not corrected later. By late 1940, Chrysler had reduced tank assembly from a craft to a sequence. Every assumption about military manufacturing had been challenged. Every tradition had been tested against time, and remarkably, the Army agreed to let them try. But there was one final problem that no production method could solve. There was nowhere to build the tanks. If tanks were going to be built differently, they needed a place designed for that difference. In November 1940, the Army issued a contract unlike anything it had ever approved. Chrysler would not simply build tanks, it would design, equip, and operate an entirely new factory, paid for by the government, but run by civilian industry. There was one condition. The factory had to be designed by Albert Kahn. Kahn was 71 years old, a German-born immigrant who had arrived in Detroit as a child. He had never attended architecture school. Instead, he had spent a lifetime designing factories that behaved like machines themselves. His buildings maximized light, minimized wasted movement, and allowed production to flow without interruption. Ford's Highland Park plant, River Rouge. Nearly one-fifth of all architect-designed industrial factories in the United States bore his influence. Kahn understood immediately that this was not a normal construction project. The building needed to be massive. It needed to be built in months. It needed to survive air attack, and when the war ended, it needed to be converted back to civilian use. He designed the Detroit Arsenal tank plant as a single integrated system. Under one roof, raw steel would enter at one end. Finished tanks would leave at the other. Between them, a quarter-mile-long assembly line would carry hulls forward at a fixed pace. Feeder lines would deliver engines, suspensions, turrets, and transmissions at precise intervals, timed to the minute. The building itself reinforced the process. Reinforced concrete replaced steel framing, allowing faster construction and wide, column-free spaces. Thick walls and blast-resistant roofs added protection. Natural light flooded the floor, reducing fatigue and mistakes. One feature mattered more than all the others. The main assembly line was sunk 4 feet below floor level. Tanks moved through a shallow trench, allowing workers to access undersides without lifts, pits, or delays. Suspension systems, drivetrains, and final fittings could be installed faster and more safely. A single architectural decision saved hundreds of labor hours per vehicle. On September 9, 1940, ground was broken on farmland north of Detroit. The schedule was brutal. The factory would not be finished before tanks were due. But Kahn's design assumed something critical. The building did not need to be complete for production to begin. And that assumption would soon be tested in the coldest possible way. By the winter of 1940, the Detroit Arsenal tank plant was still a construction site. The walls were only partially finished. Windows had not yet been installed. Entire sections of the building stood exposed to the Michigan cold. The heating system existed only on blueprints. And yet, Chrysler began building tanks anyway. By February 1941, machine tools were arriving by rail and being installed while concrete was still curing around them. Assembly fixtures were bolted into place as construction crews worked overhead. Electric cables and compressed air lines were routed around men who were already preparing production stations. It was not orderly. It was not comfortable. Temperatures inside the building regularly dropped below freezing. Workers wore heavy coats and gloves while handling steel components. Their breath hung in the air as they tightened bolts and aligned assemblies. Oil thickened, metal shrank. Nothing about the environment was forgiving. To keep the line moving, Chrysler improvised. A steam locomotive was rolled directly into the unfinished factory. Its boiler ran continuously, flooding the immediate work area with heat. Steam drifted through the cavernous space as tanks took shape beneath bare concrete beams. It was an image that captured the entire program in a single frame, a locomotive warming a tank factory that did not yet exist. There was no ceremony, no announcement, just work. Schedules were rewritten weekly. Problems appeared daily. Every delay threatened to collapse the timeline, but something unexpected happened as the line began to move. The system held. Because the parts had been designed to fit, they did. Because tasks had been simplified, new workers learned them quickly. Because the process was planned end to end, progress continued even when conditions were miserable. This was not careful planning executed perfectly. This was industrial willpower forcing reality to cooperate. And while the buildings slowly closed around them, the tanks kept moving forward, station by station, proving that the method worked even when everything else was unfinished. The walls would come later. The tanks could not wait. Once the first tanks began moving down the line, the next enemy revealed itself. Bottlenecks. No production system fails all at once. It fails one operation at a time. A delay at a single station ripples forward and backward, slowing everything behind it. Chrysler's engineers watched the line relentlessly, measuring where time disappeared. And then they attacked those moments without hesitation. The transmission was the first major obstacle. In Arsenal production, it had been built piece by piece inside the hull. Shafts were aligned by hand, clearances were adjusted repeatedly. Assembly alone consumed nearly 40 labor hours. Chrysler redesigned it completely. The transmission became a self-contained unit, assembled on its own dedicated line. It was tested, sealed, and delivered to final assembly as a complete module. Installation dropped from days to minutes. What once took 40 hours now took 4. The suspension system followed. Instead of building it directly onto the hull, Chrysler standardized every component. Entire bogie assemblies were pre-built, inspected, and stockpiled. Workers no longer assembled suspensions. They bolted them on. 2 hours of preparation, 20 minutes of installation. Each change removed judgment from the process and replaced it with sequence. Welding, once feared as a bottleneck, became an advantage. Armor plates were positioned by heavy jigs that locked angles and spacing in place. Welders followed fixed paths. Quality depended on procedure, not artistry. New operators reached acceptable standards in weeks. Training shifted accordingly. Workers were no longer taught to build tanks. They were taught to perform one task perfectly. A man assigned to install transmission mounts practiced on fixtures for 2 days before ever touching a real hull. By the time he reached the line, his movement was automatic. Every improvement compounded the next. As bottlenecks vanished, the line stabilized. As the line stabilized, output increased. As output increased, confidence followed. By early 1941, something unprecedented was happening inside the unfinished Detroit arsenal. Tank production was no longer limited by craftsmanship. It was limited only by how quickly engineers could find the next place where time was being wasted. And there was one final bottleneck that could not be solved with jigs or training. The engine simply did not exist in the numbers the war demanded. For all its progress, the Detroit arsenal still depended on one component Chrysler could not control: the engine. The Army's preferred power plant was the Continental R975, a radial aircraft engine adapted for armored vehicles. It was reliable, powerful, and already proven. It was also impossible to obtain in the quantities required. Continental simply could not build them fast enough. Every tank without an engine was a dead end on the assembly line. Production could be perfect, workers could be trained, bottlenecks eliminated. But without engines, nothing moved. For the first time, the Chrysler method faced a problem that engineering efficiency alone could not solve. The solution that emerged sounded absurd. Chrysler engineer Harry Wilson proposed combining 5 automobile engines into one. Each unit was an inline 6-cylinder engine Chrysler already knew how to build. Individually, they were unremarkable. Together, linked through a central gear case, they could drive a single output shaft. 5 engines, 30 cylinders, 1 power plant. The Army hated the idea immediately. It looked complex. It looked fragile. It looked like something designed on paper, not for war. Officers called it a contraption. a Rube Goldberg solution to a serious problem. But complexity was not the same as impossibility. The multi-bank engine used existing tooling, existing workers, existing supply chains. Nothing exotic was required. Each sub-engine could be built on lines Chrysler already operated, then assembled into a single unit by semi-skilled labor following fixed procedures. When completed, the engine produced over 400 horsepower, more than enough to move a 30-ton tank. It was bulky, unconventional, and unlike anything the Army had ever approved. It was also available now. In wartime, preference matters less than delivery. With no alternative that met the timeline, the Army relented. The multi-bank engine entered production under protest, not enthusiasm. It was not elegant, it was not loved, but it solved the problem that mattered most. The line could keep moving. And with engines finally arriving in volume, the moment of proof was no longer theoretical. It was days away. On April 12, 1941, one day before Easter Sunday, the Detroit Arsenal tank plant was still unfinished. Sections of the building lacked walls, windows were missing, the heating system remained incomplete. Construction crews and production workers shared the same space, stepping around each other as steel moved slowly down the line. But on the factory floor, something unprecedented stood complete. The first tank built by Chrysler. It was an M3 medium tank, 28 tons of steel, armed with a 75mm gun mounted in the hull and a 37mm gun in a rotating turret. Even as it was finished, the design was already a compromise, shaped by urgency more than theory. None of that mattered. What mattered was how it had been built. This was the first tank in history produced using an automobile-style assembly line, not crafted, not individually fitted, assembled step by step by a system that did not depend on any single worker's judgment. 12 days later, on April 24th, the Army arrived for the formal demonstration. Executives, officers, politicians, and factory workers gathered outside the still incomplete building. K.T. Keller climbed into the tank himself as it rolled out into the spring sunlight. It accelerated across the proving ground, crushed obstacles, fired its weapons, and drove straight through a mock farmhouse constructed for the test. The message was unmistakable. Speed had not weakened the machine. Mass production had not sacrificed capability. Behind that single tank stood something far more important than armor or firepower. The assembly line was operational. Component production was synchronized. Workers knew their tasks. Suppliers were delivering on schedule. The system existed, and it worked. What had begun as a gamble was now a demonstration. America could build tanks this way, and now that it had proven it could, the only remaining question was how fast it could do it again. Once the system was proven, speed became the only remaining objective. In May 1941, the Detroit Arsenal produced a tank every other day. By June, one rolled off the line daily. In July, 2 tanks per day became routine. Each increase exposed new limits, and each limit was attacked the same way. Production was no longer about heroics. It was about flow. A single tank required nearly 8,000 individual components. Chrysler could not build them all in-house, so it built something else instead, a network. Engineers fanned out across the Midwest, then across the country, recruiting suppliers who had never touched military hardware. The offer was simple. Chrysler would provide specifications, tooling assistance, and guaranteed contracts. In return, suppliers would deliver parts on time, in volume, to exact tolerances. Foundries in Pennsylvania poured final drive housings. Machine shops in Wisconsin cut track pins. Forging plants in Ohio shaped armor components. By the end of 1941, more than 400 companies in 32 states were feeding the line. Inside the factory, the culture changed with the numbers. Daily production totals were posted where everyone could see them. Workers knew exactly how many tanks their shift had completed and how many the previous shift had managed. Friendly competition emerged, not for recognition, but for output. Bottlenecks were no longer tolerated. Teams of engineers monitored every station, every hour. If a delay appeared, it was isolated, analyzed, and corrected immediately. No fix was too small. No assumption was beyond question. Training kept pace. Thousands of workers with no prior experience were absorbed into the system. They did not learn how to build tanks. They learned how to perform one task correctly, repeatedly, until it became instinct. By late 1941, the Detroit arsenal was no longer experimenting. It was accelerating. Production itself had become a weapon, one that did not fire shells, but determined how many shells would be fired, how many vehicles would move, and how many losses could be replaced. And soon, the scale of that weapon would shock even the people who had built it. By the end of 1942, the Detroit Arsenal tank plant no longer resembled an experiment. It was a machine in its own right. Production increases that once felt dramatic had become routine. The assembly line moved with mechanical regularity. Tanks advanced from station to station on a fixed schedule, pausing only long enough for each task to be completed before moving forward again. Then December arrived. In that single month, the Detroit Arsenal produced 896 tanks, nearly 30 tanks per day. No other tank plant in the United States came close. In fact, the output of this one factory exceeded the combined production of all other American tank plants and surpassed the entire German tank industry. The scale was almost incomprehensible. Every 55 minutes, a completed tank rolled off the line, each one identical in its essentials, each one repairable with standardized parts, each one ready to be shipped, crewed, and thrown into combat without delay. The tank itself was the M4 Sherman. It was not the heaviest tank of the war. It was not the most heavily armed. German designs like the Tiger and Panther outmatched it in armor and firepower. Sherman crews knew this better than anyone, and they paid for it in blood. But the Sherman had advantages that mattered more. It started. It moved. It could be repaired quickly. When it was lost, another one arrived to replace it, and when entire units were destroyed, they could be rebuilt in weeks rather than years. This was the logic of production made visible on the battlefield. Germany built better tanks in isolation. The United States built better systems. By December 1942, the outcome of that difference was already being written, not in factories, but in the steady, unstoppable arrival of armored units that could not be exhausted. The Detroit Arsenal had not just met the impossible goal set 2 years earlier. It had redefined what was possible in modern warfare. By the time the war ended, more than 22,000 tanks had rolled out of the Detroit Arsenal tank plant. Nearly 1/4 of all American tanks built during World War II came from a single site north of Detroit. They fought in North Africa. They landed on the beaches of Normandy. They crossed France, pushed into Germany, and island hopped across the Pacific. Many would continue fighting long after the war ended, serving in foreign armies for decades. But the tanks themselves were not the most important thing produced there. Before 1940, every major power believed armored warfare depended on specialized factories, master craftsmen, and slow, deliberate production. After Detroit Arsenal, that belief was gone. Tanks were no longer sculptures, they were products of systems. The true weapon Chrysler built was not steel or firepower, it was a method. Way of thinking that treated war as an industrial problem and solved it with industrial discipline. Parts became interchangeable. Workers became scalable. Experience was embedded in design instead of individuals. That shift changed everything. It meant armies could be rebuilt as fast as they were destroyed. It meant losses could be absorbed instead of becoming catastrophes. It meant that time itself could be bent by organization, planning, and engineering confidence. When K.T. Keller answered the phone in June 1940 and said he had never seen a tank, he was not admitting weakness. He was admitting something more dangerous, that he was willing to figure it out. By 1942, a tank rolled off the line every 55 minutes, and in that steady rhythm, steel, motion, repetition, the United States found the advantage that would carry it through the war. If you found this story worth remembering, consider leaving a like. It helps preserve the stories that didn't fire the shots but made victory possible.